relations like computer modeling, tissue engineering, biophysics, biosensorics, and it applies mechanical, electrical, chemical, and optical, and other engineering principles inside the biomedical engineering. Let's say the department or the biomedical engineering branches are broad all over the world. So at MIT, at Stanford University, and Stanford, I would like to maybe a little bit highlight, because Stanford was first university in the States that started with startups and with the commercial side connected with university. So that's what we are starting here in Slovakia. We are trying to connect the university with the application. That's why we are trying to make a new company, even if there is a new development, like for bioreactor. We are now in a phase that we are trying to develop bioreactor, and we are starting a new company. So the titanium custom-made implants also, it has a company. Dental products has a company, and it's close cooperation with university where the R&D can be produced. So I would like to start with the manufacturing technologies. We are using more than 25 3D printers here at the university with a lot of principles. So FDM, SLS, SLM, DMLS, EBM, SLA, DLP, MJ, and binder jetting. What is expected in 10 years? It's everything is going to regenerative medicine and personalized medicine. So we are expecting that in 2030 we will be able to produce functional organs, let's say simple organs, not very difficult like liver, but we will be in 2030 we can print. We will be able to print, for example, vessels, all the vessels with all the perimeters. So there are 2 points: medical additive manufacturing and bioadditive manufacturing. The difference is the bioadditive manufacturing uses biomaterials, cells, and proteins, which can be printed, and medical additive manufacturing uses just the materials, the inorganic materials, and trying to mimic the tissues and organs and the systems. Why medical AM? From the product, material, technological, and recycling point of view, the same advantages as an industrial AM production, but we have the possibility to design and manufacture personalized implantable devices, respectively surgical instruments, optimization of the surgical processes. There are visible benefits in tissue engineering and 3D organ and tissue manufacturing, and it accelerates healing processes, and it's also accelerate the delivery of the implants and medical devices. For example, our typical cranial implants last for 2 weeks from the DICOM to delivery to the surgeon. So this is the methodology of the production of patient-specific implants. So we are getting or gathering DICOM data, then we are producing reference model, which is consulted with the surgeon. Then we are producing the CAD model of person-specific implant. Then we generate the STL model, produce on the machine SLS or SLM. Then we do the post-processing and packaging. Then the implant is coming to the hospital, where the implant is sterilized and PSI is ready to use. So the principle is also mentioned here. Then in this diagram. So this was the first cranial implant. The aim of the implant was to functionally and aesthetically heal the cranial defect, and also the patient was at the wheelchair after the implantation of the patient-specific implant. He is walking again. He is now in a very good condition. So this was the first implant in 2013, where the team composed from clinicians and biomedical engineering at the theater, which is now common. So all our guys which are connected with the CAD modeling are at the theater when their intervention is proceeded. So this was the second one. Here we have also the implant which is coming inside the maxillo-facial region. So I put it also there. So nearly the similar as the first one. This was the bilateral implantation. So also at the implant was in the region of arc and ocular arc, and it was both-sided. Again, this was the trauma, which was the skull was crushed, superior to the superciliary arc, shattering trauma. There was an acute surgery, removal of splinters, and the intracranial space for living has brain increased. Reconstruction of the orbit, ceiling, and the creation of superciliary arc using titanium plate. The patient was athlete, running regularly before and after the accident. He was almost chained to bed with obvious speech disturbances. So the aim of the implant was to reveal this patient. So this was the phases of the planning, and then the surgery. So this patient was running again after using our implant. This was the implant, which is in a Autodesk, let's say, advertisement for Fusion 360. This is the biggest implant for the maxillofacial region. Right now the patient is good. He received also the mandibular device. There was he is planned for two another operations, because the problem is with skin. The skin needs to be stretched because the implant is rigid, but he's in a very good condition. He's taking care of the implant, so he needs to have a scheduled regime how to be with the implant, but his perspective in 2 years is that he will be without any care, any extra care with the implant. So he needs to he has a regime in the summer because the implant is thermoductive, so he cannot be at the higher temperatures, more than 30 to 34 degrees for a long time, because he is inducted with thermal, but the patient is good. Then we have a specialty. This was a young lady with tumor. There was a necessity of resection. More than a half of the bone tissue in the sledge area. There was a need for adjustable modular implant. So the aim was to biomechanically and aesthetically replace the defect. So we prepared this adjustable mandible. with the butterfly for the X-ray, so the girl can see on X-ray every time when she's radiated, she can see the butterfly there. This was a TMG implant, so also with the PE joint and the implant was from titanium and the joint was from PE. This was another implant for very small patients. So this is the patient with palate cleft, and the implant was made before the child was born. So we've met the mother. We've got the data from CT and MRI, and we've prepared an anatomical device which fits anatomically to his palate. And then after the delivery, we were there in the hospital. We put the device on, and then the mother could breastfeed the child. So she was very happy, and the final results was unbelievable. And I prepared also our different approaches for different regions just in a short time. This is the patient-specific thoracal implant. So we are preparing also the implants for thorax. Then custom-made spinal implants. So we are copying the area of the vertebrae. So the up and downs of the vertebra, and we are filling the gap with special cage which fits for each element, for each stash of the spinal cord. We are doing also the cervical and the lumbar cages, and we designed over 150 implants, and right now we implanted nearly 320 implants, custom made to Slovakia, Czech Republic, India, Brazil, Ukraine, Croatia, Italy, and also Spain. And then we are doing also topological optimization of different kinds of implant. This is the cervical implant. So topological optimization of the inner space with the special ribs, and also the anatomical optimization. And the vision for the next development is cloud computing in medicine, big data and predictive analytics, artificial intelligence, augmented intelligence, and brain-computer interface, augmented reality, medical additive production of prosthetic and orthotic tissues and organs, medical nanorobotics, telemedicine, hospitals of the future, so manufacturing hospitals. And maybe one more product which we produced last year. This is the implant for the tracheal diseases or disorders, or traumatic tracheal defects. Right now we are testing it on preclinical testing in animals, in the pigs, because this was the case study of a dog. The dog is now in my house, so I'm living with him for 2 years, 1.5 years, and he is in a very good condition. But we are trying to use this case for COVID patients which are on a ventilator, and where they have a defect on the trachea and they have a tracheal stenosis. We would use this platform, this implant, which we gave to Balu, to the dog, and we can make for them that the trachea after the implantation will be in the condition like before the ventilator. Thank you for the
Yeah, thank you, Marek, for this impressive presentation. I have already seen this or major part of this presentation at least 3 times, but I'm always impressed by your work and by your activity. I think it's really great what you can do and what you do. So what I recommend, I have seen that there were several questions, but I recommend to go through on the presentations, and at the end of the presentations, go through on the questions that we received. And I guess, and I recommend to the speakers also to check the questions and answers part, and try to respond to the questions if they can in writing. And the next speaker will be Dr. Daniel Bomze. He is the head of business unit, the medical unit at Lithos, an Austrian company. Daniel will present us an alternative to titanium 3D printing. In fact, there was a question in relation to that. And as well as recommend us, I guess, machines to buy to replace our titanium